Hi students, this is Mr. Yao. Today we're going to continue to learn more about matrix, and in the next few lessons we are going to learn a specific kind of operation that is called row reduction for matrix. Our knowledge, because row reduction is actually used to solve system equations, so let's actually quickly review system of equations. Question A, you can pause here and try to think by yourself, and then you can come back to check the answer. Saying if 2x plus 4y equals 6, that's negative 20x minus 40y equals negative 60, and is asking you to explain your answer. The answer is yes. You have a few different ways to think about this. One, well, 2, 4, 6, you can see they're related to 20, 40, and 60. So if we choose to multiply everything by a negative 10, we are going to get the second equation. So if the first equation works, the second equation has to work. That's one way to think about it. The second way you can think about it, or you can choose to go backwards and think, oh, if I divide everything by a negative 10, I'm going to get that first equation, then the left side and the right side has to be equal to each other. Here's the second way to think about it. And there's a third way. We can choose to simplify both, and they will both become x plus 2y equals 3. We'll just divide both sides on the first one by 2, divide both sides by negative 20 on the second one. And there is also a last way to think about it, which is if we choose to rewrite both into the graph y equals mx plus b form, they're both going to become y equals negative 1/2 x plus 3/2. And that also means they are the same, hence if one of them works, the other has to work. Question B, substitution, elimination, and graph are three different methods that we have learned to solve system equations. I'm going to quickly recap each of the methods, but I'm not going to finish calculating the answers. First, substitution, or in other words, replace. The process is you need to get one variable by itself so that you can replace that variable in the other equation. And in this case, x is very easy to get by itself, so I'm going to do that. X could be rewritten as 2y plus 2. I just add both sides by a 2y, and now I'll be able to represent x using y. Now that I can see x is 2y plus 2, I can replace any x that I see by 2y plus 2. That's where the substitution comes in. I'll make the equation into 3 times 2y plus 2, then minus 5y equals 9. You can clearly see that I only have an equation with y. I can solve for y, then I just need to put it back to find the corresponding x. That's the substitution method. Next, we have the elimination method, or in other words, get rid of or take away. So we need to make something cancel with each other so you can eliminate that. Let me copy down the two equations again. X minus 2y equals 2, or 3x minus 5y equals 9. We want to be able to have opposite numbers, so we can just, when we add them together, they are eliminated, they are taken away, they're gotten rid of. And in this case, 2y and 5y clearly not the easiest because that means you have to change both into a 10. So the x would have to be the easier one to use. I'm going to multiply the first equation by a negative 3. The reason I multiply by a negative 3 is because then I can get a negative 3x, which can cancel out with a positive 3x. So this equation now becomes a negative 3x plus 6y equals a negative 6. Now if I choose to add both equations, the x's are gone. I'll have a negative 5x and a positive 5y and a positive 6y add together to equal just a y. That equals to a 9 minus 6, which is a 3. You may not always just get right to y. Maybe you end up with like 3y equals something. Well, then you just need to divide both sides by a 3. You will find the y. And then you can just plug back into either equation to find the corresponding x. Lastly, the graphing method. Whenever we want to graph an equation, we would have to rewrite it as y equals mx plus b. Or in other words, you need to solve for y so that you can actually graph them, and then you are going to find the intersection. So these are the three methods that we have learned before to solve system equations. So in this lesson, we are going to get started to introduce you on how to use matrix to solve these system equations. But before that, we need to learn something called row reduction, so I can use that operation for systems. Above is something we have learned, system equations, and more specifically, it's a 2x2 system, which means it has 2 equations and 2 variables. You can see things get complicated. Imagine if you have 3 equations and 3 variables. They will get very complicated, no matter which method you try to use. And that's how we're going to learn matrix, because it's an easier way. The more complicated the system is, the easier matrix method will be. In the process of solving, you may have noticed that we wrote x and y quite a few times. What if we can organize the numbers in a neatly fashion so that we don't need to write x and y, and that's where we're going to use matrix. So to begin with, we need to understand how different type matrix are related to the system of equations. Coefficient matrix. That is a matrix formed by the coefficients, typically on the left of the equation, and that's referring to our typical x and the y. Then we have the answer matrix, a matrix formed by the answers, typically on the right side of the equation, or in other words, equals to those numbers could actually form an answer matrix. But we're actually going to use neither of them. We are actually going to use both of them together, because either of them is going to be super helpful since we do need the whole system. That's where we have augmented matrix. That's a fancy word of saying an add-on. It's a matrix formed by joining the columns of 2 or more matrices that have the same amount of rows. And since both the coefficient and answer matrix will come from equations that we have, then of course, however many equations we have, however many rows we may have, then we will have this augmented matrix. In our lesson today, we're joining the coefficient matrix and the answer matrix to form the augmented matrix, and we usually put a line between them. Now let's actually practice writing down some augmented matrices. First, for example 1, I will show you the coefficient and the answer matrix, but again, our goal is to actually form the augmented matrix. So for 1, coefficient matrix. That means I just need to copy down all the coefficients. That will be 1, -2, 3, -5. Just all the coefficients for x and y. As for the answer matrix, that of course would be the answer side. So 2, 9. Lastly, which is the augmented matrix, that's the one we are going to be using. We just join these two, so 1, -2, 3, -5. We're going to draw a line to tell ourselves, hey, everything to the left, they're coefficients, and everything to the right, they are our answers. This augmented matrix is quite specific. So let's have a look at example 2. X, y, 1, 2, x, y, -1, 1. On the right side, we have the answers as -5 and 3. For example 3, the first equation, you will see there's no y, but technically that would just be a 0y. So even if we don't have a number, a coefficient for a certain variable, we still need a 0 as a placeholder. So we have 3, 0, and then 5, -3. On the right side, we have 2 and 6. Something else I want to emphasize on, the reason we can choose to write them into matrices and without writing the x, y, z, or in the future maybe more variables, is because the matrices are already formed in a very specific way. This column represents all the x, that column represents all the y, and that column represents all the answers on the right side. So that means even if, let's say, I rewrite this equation, let's say you are given an equation like -3y equals -5x plus 6. That won't change your matrix. You won't suddenly have like a -3, -5, and then 6. That still doesn't work. Because the matrices, you have to form them to make sure that your x and y are both on the left side and just the answer on the right side. They have to be in that very specific order. Now let's talk about row reduction. Row operations. Since matrix keeps the number organized, we can now solve the system equations using row operations. And they are used in a branch of higher mathematics called linear algebra. But all we need in this section is actually to get used to the different kind of operations that we can do to these rows. The first option is interchange any 2 rows, which is called row swap. Next, you can replace a row by a non-zero multiple of that row. Here's the thing, non-zero. That is very important. Because if you multiply the whole row by 0, you just get a bunch of zeros, which actually won't do anything. This row of 0 doesn't help you with solving the system equations. So we will never multiply a row by zeros. But you do have the option to multiply that row by any other numbers that are not zeros. The last operation that we can do with rows is called replace a row, is called times row add. That means replace a row by the sum of that row and a constant multiple of another row. This may seem very complicated. By the words, we'll see how that works when we get to the examples. But to keep track of what we're doing, we're actually going to need to use some notations. We are working with 2 by 2s, so we have 2 rows. That's why we're going to name them as R1 and R2. Here's the notation to represent row swap. Swap just means you switch them. So that means R1 and R2 are switching places. That's where we're going to use a double-sided arrow to indicate R1 is becoming the new R2 and R2 is becoming the new R1. We're just switching them. Next, times row. Just like the name, you're going to multiply the row with a number. Let's say you multiply with the row with a 5. Just like say you multiply an x with a 5, you're going to get like a 5x. Same thing here. When you multiply a row, let's say the first row by a 5, you're going to write it as 5R1. Lastly, times row add. This is the more complicated one. When we multiply a row by a constant, let's say -2, that row will just become, let's say you multiply by the second row, that row will just become -2R2. And add onto another row. So we're adding it onto row 1. And we'll know the last row in the operation is the row that will change. So again, this is our operation. Sometimes you will see that. That also indicates to you that you are changing R1, or you may not see that. You may just have -2R2 plus R1. No matter what, the last row that is mentioned in there is going to be the row that you are changing. So again, this to translate into words means you're going to use row 2 multiplied by -2, then you're adding it onto row 1. So my row 2 does not change. That is very important. Now let's see these operations in a few examples. First one is simple. Well, row swap is the simplest because all you need to do is just switch them. So let's actually talk about the other ones. But first, you do need to actually write down the augmented matrix. For example, for 3, -9, 2, -5, right side we have -9 and 4. And clearly, this is our first row. And this is our second row. The question said 1/3 times row 1. That means I'm going to multiply everything in the first column, in the first row by 1/3. And I will get a new matrix. 3 times 1/3 is a 1. -9 times 1/3 is a -3. -9 times 1/3 is another -3. But I didn't do anything to the second row, so I'm going to copy it down. 2, -5, 4. That is my second row. And that is the whole thing after the operation of 1/3 times row 1. Example 5, same thing. Let's start with the augmented matrix. 1, -3, -3, 2, -5, -4. And we are going to first make sure you understand this notation. That means you are multiplying row 2 by 2, then you're adding onto the first row. So you got to be clear, row 2 is not changing. I'm going to copy down row 2 first. 2, -5, -4. And then, since I need to multiply that by 2 and then add on to row 1, you can choose to write some smaller numbers to indicate to you the first operation is multiply by 2, times that by 2, times that by 2, times that by 2. I will get 4, -10, and -8. And then I'm adding these numbers onto the first rows. That is a 4 plus 1 is a 5, -10 plus -3 is a -13, and -8 plus -3 is a -11. And that is how we do row operation. Now you can pause here to try example 6. Now let's come back and have a look. First, gotta write the augmented matrix correctly. First row is 1, -3, and on the right side is a -3. Second row, we do not have an x, so it's just a 0 for the first column, and then it's a 1 for the 1y, and then it's a 2 on the right side. Again, you gotta make sure the x and the y and the numbers are lined up this way so you can write the augmented matrix correctly. Now let's have a look at the operation. Row 2 multiplied by a -3, row 2 multiplied by a -3, and then I'm going to add that onto row 1. So again, I'm not changing my row 2. 0, 1, 2. But I do need to multiply that row by -3. So I will get a 0, a -3, and a -6. And I'm adding these numbers onto the first row. 0 plus 1 is 1. -3 plus -3 is -6. Negative 6 plus negative 3 is negative 9. That is how we do row operations. And in the next lesson, we are going to use these row operations to actually solve system equations. Thank you.